A container in the shape of a right circular cylinder with a top has surface area 2 pi square feet. What height h and radius r will maximize the volume in the cylinder? So we've got a cylinder. We should give a sketch of it. It's going to look something like this with a radius and a height. And we want to maximize the volume in the cylinder. Do you know the formula for the volume of a circular cylinder? Well, the volume is going to be the area of the base times the height. The area of the base is going to be pi r squared, because it's a circle, times the height, which we said was h. Now, we can't deal with this like it is, because when we want to find the critical numbers, we're going to have to differentiate, and we need volume to be a function of just one variable, not two. But we have a piece of information we haven't used. The surface area is 2 pi, and we can use that to find a relationship between the radius and the height, so we can solve for one of those in terms of the other. So we know the area is 2 pi square feet. And if we want to find the area of that, we need to add together the area of the different surfaces. Now, the top and bottom are both circles, and the area of those is going to be pi r squared for each of them. So that's going to be 2 pi r squareds, one for the top and one for the bottom, plus this vertical side. If this was a can of soup, that would be the side that the label is on. And that's actually a rectangle, right? It is wrapped around in a circle, but if we were to cut that open and unwrap it, it would be a rectangle. We know that we've got rectangular labels that go on most soup cans. And so the area of a rectangle is the base times the height, but the base of that is actually the circumference of the circle. It goes all the way around, and the circumference of a circle is 2 pi times the radius. So that's going to be 2 pi r. That is the circumference, which is the base of that rectangle, times the height of that rectangle, which is h. And we know that that area is going to be 2 pi in total. Now, there's a lot going on here, but notice that all of these terms are divisible by 2 pi, so we can divide both sides of this equation by 2 pi to simplify it. If we do that, that gives us r squared plus rh equals 1. And the easier variable to solve for here is h. So I'm going to subtract r squared from both sides, giving us rh equals 1 minus r squared. And then to get h alone, we divide by r. So that's going to be 1 minus r squared over r. And we can substitute that in for h in the volume so that we can write that only in terms of the radius. So that means we've got v equals pi r squared times the height, which we said was 1 minus r squared over r. We can cancel out the r in the denominator with one of the r's in that r squared, giving us v equals pi r times 1 minus r squared. And we can leave it like that, or we can distribute the pi r. I'm going to distribute the pi r because we're going to need to differentiate, and it's easier to do that term by term. So that's going to be pi r minus pi r cubed. And so once we have that, we've got volume as a function of just the radius. We can take the derivative of that, and that is going to help us figure out our critical numbers and hopefully find the values that give us a maximum volume. So the derivative of pi r is just pi, and then minus pi times the derivative of r cubed is 3r squared. And so that is our derivative. If we're looking for critical numbers, we want to know when this is undefined or equal to 0. It's never undefined, but we can set it equal to 0 and solve. If we factor out a pi, that's going to give us pi times 1 minus 3r squared equals 0. And we know that the left-hand side is going to be 0 when 1 minus 3r squared is 0. So we need to solve 1 minus 3r squared equals 0. We can add 3r squared to both sides and then divide by 3 to get the r squared alone. And when we take the square root, we've got the square root of 1/3. We don't need to worry about the negative square root of 1/3 because the radius can only be positive. Doesn't make sense to have a negative radius. So this is our critical number, and it's probably going to end up being the value that maximizes volume. But let's make a quick sign chart for our derivative so we can see what's going on with our function. We've got the square root of 1/3. All right, and what do we have? We've got pi, which is always positive, and we've got 1 minus 3r squared, and we want to know when that is positive or negative. If r is really big, then the 3r squared is going to be really big, and so we're going to be subtracting something large from 1, and that's going to be negative, and then it's going to be positive when it is smaller. We're ignoring anything less than 0. And so we can see that our derivative of volume is going to be positive and negative. So volume will be increasing and then decreasing. So we're going to have a maximum at our critical number. And notice that that local maximum has to be a global maximum because on the domain of positive numbers, the volume is increasing and then decreasing. And so that has to be our maximum. So we wanted to know the height and the radius that maximize the volume. We've got the radius. It is the square root of 1/3. To find the height, we need to plug that in. And we've got h is 1 minus r squared over r. So that's going to be 1 minus the square root of 1/3 squared all over the square root of 1/3. Well, the square root of 1/3 squared is just 1/3. So we've got 1 minus 1/3 over the square root of 1/3. 1 minus 1/3 is 2/3. So 2/3 divided by, we can rewrite this as the square root of 1 over the square root of 3. Makes it a little bit nicer because when we're dividing two fractions, we can multiply by the reciprocal. So that's going to be 2/3 times root 3 over, the square root of 1 is just 1. And so that's going to be 2 root 3 over 3. That is the height. So we wanted to know the height and the radius. The height is going to be 2 root 3 over 3 feet, because everything here is measured in feet. And the radius is the square root of 1/3 feet. And I imagine you don't know exactly what that height and radius actually means. So we might want to get a decimal approximation for each of these. The decimal approximation for the height is about 1.15 feet. And for the radius, that's going to be about 0.58 feet, which is just a little bit easier for our brains to process because we don't know off the top of our heads what 2 root 3 over 3 feet actually means. So this container would be a little bit over a foot tall, and the radius would be a little bit more than half a foot. And that maximizes the volume.